ability to ramp up temperatures, cure with temperature, and then allow it to cool slowly over time. And so this flight controller joystick that you see in the image here on the left, you can see light coming through, and that's because it was cured a little bit more of a stress environment. So this is AMX Rigid Black. It again is a new acrylate-based material. The advantage of these materials is long-term stability over time. So properties-wise, unlike epoxy-based resins that we have used for many years, they stay stable. They don't continue to cure and get more brittle and stiff, but like we've seen with some of the older resins. But the downside of that is acrylates do want to curl, they want to distort a lot more. So really to get the full benefit out of these new materials, it requires a little bit more control when you cure or do that post-cure. So you can see the part on the right, we're able to hold that gap much closer. You don't see as much light coming through there. So then the last part I think I have on my list here, is 3D Sprint. So if you go to the next slide here, 3D Sprint is our preparation software. We use this same software for many of our print engines. It really is a one-stop full solution package. To give you a little bit of history, we started out with preparation softwares for many years where if it didn't help me go from an STL file to vector data that my machine can understand and build me a three-dimensional part, we probably weren't going to include it in that software. So we didn't have the ability to cut parts or shell parts or label parts or anything like that. It was very, very much a one-purpose piece of software. In the last decade or so, actually probably a little bit longer now, with the introduction of 3D Sprint, we've started adding quite a bit more tools into that preparation software. So we do quality analysis where we check for trap volumes and features that are too small to print and things like that, to being able to measure parts, making copies and scaling, obviously, being able to place parts very easily, orient parts for best surface finish supports, manually be able to orient. You can label your parts in here, and the labeling is even smart enough to hold the curve of the part, and you can embed it or extrude it. You can split and cut parts. You can go simple cuts. You can do dovetail cuts. You can add holes and pins for joining the parts later. Adding vents and drains in the quick cast build style. Support generation is huge. Editing supports is much simpler. If anybody on this call is still using 3D Manage or 3D Lightyear, it's time to step up 3D Sprint. You can purchase a version that will run even your old legacy machines, and you can see what advantages you have with a modern support algorithm that doesn't make you edit supports one region at a time. You can actually adjust support points on your part, redraw your supports automatically. It's actually really a pleasure to use compared to what we used to have to work with. Optimizations are all there. The ability to set offsets and consumptions and estimates, and being able to manage your queue so you can actually see all your printers listed in a queue and see a machine status and see where that particular machine is in your print. All that's part of 3D Sprint. And that is all for me.
Thanks, Steve. Really good overview there of the SLA 750. Just to introduce me again, I'm Rich Broad. I'm the product manager for materials here at 3D Systems. My background is largely actually on photopolymers, and I started out with SLA back in the mid-1990s. So I want to try and kind of impart some of some of what I've learned over the years and kind of talk to you about how we're addressing, you know, materials for the latest generation, this latest generation of SLA machines. You know, as Steve noted right at the start, you know, this is the oldest technology for additive manufacturing, as we call it now, or rapid prototyping as it was then. You know, the most developed, still gives you the most accurate, you know, good detailed parts that, you know, that you'll get from an additive manufacturing process. And you know, really the way that I start to talk about materials is generally about when people are looking at additive manufacturing approaches. It's really the part in hand at the end of the process is what really counts, in terms of what it is that the whole solution is delivering. Now, of course, Steve has given you a lot of detail around the SLA 750. You know, that is an amazing platform to deliver the kind of materials that we're aiming to make available for the system and have available for the system right now, to push the solutions on to open it up to much more applications around production type environments. Of course, every additive manufacturing technique has its place in terms of what it's most suited for in some kind of production spaces. SLA, we know, is not the ultimate manufacturing solution in every scenario, but it fits a lot more than some others do. So I'm just going to dive in here a little bit on materials and perhaps take a little bit of a step back, just kind of set the scene a little bit about what we're talking about here from a materials perspective on various different technologies. So if you go to the next slide, please, Elisa. So the fundamental thing I like to make clear here is about, you know, what the key difference is between what an SLA machine will do and what we're looking at kind of moving into the space of in terms of production type materials, right? You know, if we consider who's actually going to be specifying the kind of materials that will be an SLA machine will be producing, it's going to be design engineers, material specifiers, those kinds of people that will want to see a thermoplastic-like part, or expect a thermoplastic-like part, or expect a machine to deliver a part that behaves essentially like a thermoplastic. So a thermoplastic is a material that is a thermo-softening material, essentially. So you melt it. You know, the most common technique is, you know, injection molding or blow molding or rotational molding, whatever. So you're melting a material beyond its melting point. It becomes fluid. You're injecting it or casting it into a cavity, and then it's cooling and solidifying again, or crystallizing in some way, shape, or form. And those are generally materials that are used with very well-known additive manufacturing techniques alongside some of the traditional techniques. So those additives being SLS at relatively low temperatures, powder bed fusion, or FDM, so extrusion-based machines, essentially. And of course, you know, 3D Systems has SLS and extrusion via Titan, or the medical-based systems through Camovis. Next point, please. What we're talking about here is essentially thermosetting polymers. Now, these are fundamentally different, obviously, from thermoplastics. It's a very different way of achieving a solid part. You're actually reliant on a chemical reaction rather than purely a softening or a melting and a resolidification. You're actually relying on a chemical reaction to change from a liquid .
Bienvenidos al seminario web. Ha entrado como asistente en modo de solo escucha.
In this case, are used in all of those technologies that use UV as a mechanism to initiate that chemical reaction to achieve a solid part. Now, excuse me a minute. essentially, I mean, if we talk about innovation, generally with thermoplastics, there's a relatively low level of innovation. So essentially, the reliance there is on dry or wet blending of materials for new properties to achieve something different. With thermosets, right now we're in a period of a fairly high level of innovation, particularly around what you see with some of the the projector-based machines. And what I'm going to talk about here is how we're now adopting some of that new chemistry into the SLA, the stereolithography type environment. Next slide, please. So if you look at a timeline around SLA specifically here, what this really describes is that we're moving from basic prototyping to proper additive manufacturing. Okay, so back in the day, late 1980s, early 1990s, the range of materials for SLA particularly were very crude materials. They were very simple acrylate materials, or even some vinyl ether materials, and generally had great properties in order to be able to achieve a solid part relatively quickly in the machine. So they were accommodating some of the inadequacies of an SLA machine. So essentially, SLA machines had relatively low laser power. They drew really slowly. The materials had to be fairly reactive in order to be able to achieve a net shape, if you like, coming out of the machine relatively quickly. But that meant that generally the materials had very few engineering characteristics around them. You could achieve a bit of form and fit, very little function in terms of what those parts actually delivered. So you drop a part on the floor, even a soft floor, generally the parts would break, and you were lucky if they ended up in only 2 or 3 pieces. Normally they would sometimes shatter into lots of pieces. The real step change came with SLA around the mid to late 90s, when epoxy hybrid materials came in, and that really changed things, where toughness was significantly increased. The water and humidity sensitivity was significantly better, and allowed a certain degree of post-processing, not just UV, but heat post-processing as well, to give higher heat resistance properties, so above 100 degrees C. So you're kind of opening up more applications in that sense. And then between kind of the late 1990s and now, we kind of had a period where we've been working as hard as we can with those epoxy hybrid materials to create functionality. So you've often seen in the past materials described as an ABS mimic or a polypropylene mimic, and that was really a loose description of the general properties around maybe flex modulus or elongation at break, or sometimes kind of toughness around what kind of thermoplastic they might be like. And that was as close as it got really to a thermoplastic, because as Steve has already mentioned, those materials were very good, very accurate, and they still are. They still have their place to produce very good form, fit, to some extent functional prototypes. But they have their limitation in that generally they will work very well for a period of time, but they are very reliant on a reaction that you ultimately can't control. So as I mentioned before in the previous slide, you kick off a chemical reaction. This relies on a chemical reaction that just carries on, and it keeps on and on going, whether it's in a dark cupboard, whether it's on a windowsill, outside, whatever. And that will continue. So that cross-linking will continue, and over time it will get more and more brittle and become like one of the early materials. We are now in a position, if you click again on this slide, please, we are now in a position where we've moved to acrylate materials. We're kind of doesn't mean that the epoxy hybrid materials are going away. We're now moving into a position where we want to open up, as I mentioned, open up applications for this kind of technology to more proper production type applications for that, low rate initial production or end of life production, or even particular applications. So we're introducing and have introduced now 4 materials for SLA that are based purely on acrylate. And there's good reasons for doing that, largely because acrylates have the ability to produce significant advantages in terms of mechanical properties, adding in certain elements, which I'll talk about in a little bit, that were not possible with epoxy formulations. Epoxies generally are very sensitive to certain chemical types, which means we can't formulate additional kind of characteristics into some of the materials, like high temp, for example, or super high temperature, or flame retardancy, that kind of thing. One of the really important things, and Steve touched on this a little bit, is that acrylate chemistry, once you've actually built a part and post-cured, is way more stable. Meaning that the properties don't really change significantly over longer periods of time, which again kind of gives you a much more robust solution as we move into those production applications. Next slide, please. So this is a slide that really just describes how we categorize our materials, and we generally categorize according to a material property, whether it's designed for a specific application or as a general purpose kind of prototyping material, if you like. The testing we do to qualify and create that categorization across the industry has really historically been fairly unclear and fairly poorly designed, if I'm honest. And it kind of leaves a bit of a grey area that some suppliers have either ignored and sometimes maybe exploited a little bit. The key here is that enabling additive manufacturing parts to perform in a production environment means that we need to have a range of material that are suited to everyday applications, whether that's in automotive, aerospace, transportation, any kind of industrial or electronics type of applications. The list goes on. And often it's the requirements of an engineering part that needs specific properties like resistance to external forces, such as extremes of temperature or fluctuation, impact resistance, UV moisture resistance, those kind of things. Automotive is probably one of the most demanding, or aerospace, if you like, where temperature ranges can range from -40 to 100 plus 120 degrees C. That's relatively common in moist environments. And generally what we're trying to do is move to provide that kind of information to those design engineers, to those production specifiers or material specifiers, that really give that that kind of guarantee, or the information to enable them to make that choice, to say this is a material that's good for that low rate initial production as we move up and ramp up into full production, or for other applications towards the end of life. Next slide, please. So how do we access production applications, and how do we describe our materials? So this is really the key to how we do this. We're looking for production mechanical properties, performance properties, and testing to production testing standards, right? So our aim is to produce data sheets that have consistent data. So where in the past we were looking at data sheets that are essentially at the most 2 pages long, often only 1 page, that gave very basic mechanical properties, what we've been doing for quite some years now is building out data sheets with some consistent data across materials and across platform types, in order to really describe as best possible. Of course, that doesn't necessarily mean we're going to have all of the data available that everybody's going to want. That's not that's not really feasible. But largely, this covers a very wide range of applications, and often we'll be testing a material according to the kind of applications that it's designed for. Important here is that we're testing to recognize standards, so ASTM, ISO